Hi class, this is an example video for Unit 5.2. So Unit 5.2 is just building off what we did in 5.1. It's about further simplification of a force and couple system. And I've chosen to use problem 4-131 from the book to go through to kind of demonstrate some of these principles. So here's the image from the book. Right here, we kind of have this plate and it's got these beams, these I-beams in there, and there's force on each I-beam. And kind of done a crude drawing on the board here, dimensions and everything. So we have these four forces that are all going down in the z direction. They're at different places on this foundation. And what we're asked to do is to replace the force system with a single force and specify where it intersects the plane. So in 5.1, we were replacing the system with a force and a couple. And in here, instead, what we're going to do is we're going to replace with a single force, and we're going to place that force in a specific spot so that the resultant moment is the same. This is just kind of taking the next step. It's not always possible to do this in every problem, but in this section, when it's asking you to do this, obviously they've set the problem up to be pretty possible to replace by a single force placed at just the right spot. So how are we going to do this? So just like with 5.1, first thing we want to do is we want to find the resultant force and the resultant moment. So let's start with that. So the resultant force is really easy. They're all in the z direction, so we literally just add them up. And you can do, you don't even need your calculator for that, to just say that the resultant force is minus 140 newtons in the z direction, or kilonewtons, sorry. So that's the magnitude. That's what the resultant force will be. When we replace all these with a single force, it's going to be negative 140 kilonewtons in the negative z direction. Now the question is just, where does that need to go to cause the same resultant moment? So we need to find a point to take the moment about. And so I'm just going to pick point A. So the moment about point A I can actually do this largely just without even needing to do much cross products, because everything is since all the forces are just in a single direction, it's not actually that difficult. So I'm just going to do this the old-fashioned way of just F times D, and then sticking the sign to myself. So let's look at this force. This force is a magnitude of 20. From point A has a distance of 10 meters in the y direction. So that's going to cause a resultant moment. Sorry, that's 10 meters in the x direction. It's going to cause, so force is in z, distance is in x, the moment will be in the perpendicular direction to both of those, which is y, and that's going to be in the positive y direction. So we get 20 times 10 positive y direction. So that's the moment caused by this guy. Let's look at the moment caused by this guy. So force is in x, distance is 11 meters in the y. So the moment is going to be in the x. The only question is positive or negative. And using right-hand rule, right, where I'm going to pin my wrist at the point, the axis of rotation, and point my fingers towards where the force is, and then curl them in the direction the force is pointing. My thumb sticks into the board. My thumb, I guess, really points in the negative x direction, right? It's going to cause a twist like that. It's negative x. So I'm going to say minus 20 times 11. So force times distance. And then that is in the x direction. So now let's see what next. Let's look at this guy. So, there's two components to the direction. So let's start by looking at, so 50 It's in the negative z. The distance from A in the x direction is 3. So so we have x component distance, z force is going to cause a moment in y. And if I do right-hand rule, it's difficult to do. So I go from the axis that I'm rotating about to the force, which is that way. And then my force goes down like that. And I can see that that's going to cause a moment about the negative negative y direction. So it's going to be minus force times distance. And that's the y, but this force will also cause a moment in the x direction. Right? So if I look at this distance, the 4, the x distance 4, so going from here to here, it's going to cause a positive. So I do that. This is, sorry, this is a, well, you got to be careful. Last one we just looked at is the distance was in the y, it causes an x. Now we're looking at an x distance times a z force, which will cause the twisting in y. So you can tell that that's going to cause a positive, this, so 4 times 50. Positive 1. Okay, so we've covered these 3 forces, now just this force. And it's going to look really similar to this one. It's just the distances are slightly bigger. So we are going to get, we can tell right away, it's going to be a negative. It's going to be a negative negative about the x-axis, positive about the y-axis. So it's going to be minus. So we will take the y distance, which is 13 times the force. So y distance, z force, is the moment in the x direction. And then we'll take the x distance, which is 10. And the force, so x distance, z force gives me a y answer. So then I just do all the addition. I end up with my moment about point A is negative 1020 I hat plus 900 j hat units of kilonewton meters. So that's the resultant moment. But again, we're not trying to replace this force system with the force in a couple. We're trying to replace it with a force placed at the right spot. So what are we going to do? We are going to sort of do the backwards of a cross product. So we know that the moment, right? So again, we have to place this force in a place where it's going to produce this moment. So we know that this moment is equal to an R cross an F. We know this force, we know this moment, we don't know this R. So let's solve for it. What does that get us? That gets us that negative 1020 plus 900 J, it's got to equal IJ K. So we don't know the, let's say, Rx, Ry, and we can tell just right away that there will be no Z component of this position here. And then we have the force minus 140. So we need to solve for these, right? So we should be able to do that. So we'll simplify this out, and that gets us right? So I get ry times negative 140, so negative 140 ry. J, we cover that up and we get minus rx times negative 140, so that should be positive. And so now we can just do some algebra and solve. All right, so we get that negative. We'll just look at the x components, since we know this and this have to equal each other, and this have to equal each other. So we can just do some algebra. So 1020, negative 1020 must equal negative 140 ry. So ry must equal 7.286 meters, and 900 must equal 140 rx. Therefore, rx must equal 6.429 meters. And there you go. That is our answer. So if we replace those four forces with a single force, that's a negative 140 kilonewtons in the negative z direction, and place it at 7.286 in the y and 6.429 in the x direction, then the system is equivalent, right? Our points will fill the same forces, they will fill the same moments. So that's all there really is to that. Like I said, you won't always be able to simplify it down this way, but obviously if the problem's asking you to simplify it to a single force placed at the correct position, it's going to be set up in a way that you'll be able to. So that is that for unit 5.2. As always, let me know if you have any questions. Hopefully you can find these videos helpful.